Good afternoon, folks. I guess all of you can hear me well. Yeah. Thanks for coming in. And I'm Prabath Siriwardena from WSO2. I've been with the company for 11 years and mostly working on building the WSO2 identity server. I authored a few books, and these are the two books related to this talk: Advanced API Security and Microservices for the Enterprise. Okay. So I assume you are sort of familiar with microservices, and that's why you are here, to learn about security. So if you look at the microservices architecture, it has roots in SOA design principles. Someone even will argue that microservice architecture is a SOA done right. But then again, if you look at last few years, this has evolved a lot, and it has gone well beyond defining set of design principles. It has become a culture now, right? The benefit of, or the outcome of a microservices architecture are the speed to production, and then again, the evolvability of your applications. If you follow MSA or microservices architecture design principles, you can develop and deploy applications into production and also push updates to those applications into production in a way that you have zero or no or minimal impact on the other systems or the other connected systems to your microservice. That's the beauty of the microservices architecture. So let's look into the challenges that we see in a microservices security design. How does it differ from a security design that we do for a monolithic application? If you look at a monolithic application, most probably you will have like a couple of entry points. You expose your service or the application probably over HTTP or HTTPS. And all the requests coming to your application would be intercepted centrally. And it will do the security screening, and if all good, then only you will dispatch those requests to the internal components. So once a request hits an internal component, it doesn't need to worry about doing security screening again. It will simply accept that as a legitimate request or a message. And if it wants to access users' attributes or find out who the authenticated user is, then you have a shared session object between all these components. So when one component talks to another component, it's an in-memory call. You don't need to pass user context specifically. All these components have access to this shared user session. So in a monolithic application, with respect to a microservices architecture, security design is quite simple. In the microservices world, all the internal components that you saw in the previous diagram now become distributed. And each component has to talk to other components or the other microservices in the system or the network. Now we need to worry about securing these connections, the service-to-service communication. And also, you have many entry points. Right? In a monolithic deployment, you may have 1 or 2 entry points, but now you have a large number of entry points. A large number of entry points means you have very broad attack surface. So when it comes to microservices security, we talk about 4 main areas. One is the edge security. How do you authenticate end users or systems accessing your microservices? The second one is service-to-service communication. How you secure service-to-service communication that could happen over synchronous channels like HTTP or HTTPS, or else through an asynchronous channel like using ActiveMQ, RabbitMQ, Kafka, like through a messaging or event-driven system. The third one is the deployment. So most of the time, so microservices are deployed in the container-based deployment architecture. In fact, like if microservices were born at a time where we don't have containers, then it won't be that popular like today. So in fact, microservices and containers are like a match made in heaven. So they both complement to each other nicely. The fourth one is you need to worry about the security at the development time. You need to make sure that your developers follow good security guidelines. You need to define the security best practices, and you need to make sure you occupy all the security scanning tools, static code analysis tools, dynamic testing stuff, and also make sure that you have integrated those tools to your build system. So in that way, you can get developers concerned about the security issues they introduce system, and also have a very shorter feedback cycle, right? Because the major focus of microservices is the speed to production, and if you keep on introducing security issues and you find that at the end of the development cycle, then it takes more time to fix, and also the impact is larger. So you need to have security measures to make sure you catch all those security issues at the very earliest stage in the development cycle. Okay, so these are some of the challenges. Broader attack surface we already discussed. Performance. Now, instead of internal in-process calls, we have many remote calls, right? And also, we have many entry points. Earlier, we did security screening at a central point. Now, each endpoint has to do security screening. So, all those security screening add latency to the overall performance of the system. You need to worry about those stuff when you do a security design, how you validate the message. At the interceptor at each microservice, maybe you do the security validation in a self-contained manner, or else you may talk to a security token service. It's up to use cases, but once again, if you talk to a security token service, then again, it adds another latency. Then the deployment complexities. So in a monolithic design, you only have one application. But now we may have hundreds of applications. So how you handle that? Unless you have proper automation tools, it would be a really nightmare. In terms of security, so when you have multiple workloads or multiple microservices, you need to have a way to identify each of these microservices. So you need to have a way to provision credentials to these microservices. So those can be certificates or some kind of tokens. So once you provision those tokens in a highly distributed environment, you also need to worry about how to rotate these tokens, how to revoke these tokens. So these stuff you need to worry about. And also the bootstrap trust between different microservices. You need to worry about all this stuff. Then the observability. Observability, in fact, it's a measure about the level that you can infer the internal state of system based on the external outputs, right? So there are three pillars of observability. Those are logs, tracing, and metrics. A log can be a very simple audit log, audit trail. We should probably say the order processing microservice access the inventory microservice on behalf of user Peter at this time of this day. It can be just a security event, right? So logs are basically record events. It can be any event. Then metrics, once again, they are based on logs, but they aggregate set of logs to build more useful information, which will basically show you the direction your system is heading to, right? So in the same example I took before, the number of, or the average invalid access requests. It could be a metric of your system. And if that number is high, that's an indication that either your system is under attack or else your first defense is weak. And you can also engage different triggers or alerts for those metrics. So if the number of failed access attempts go beyond a certain level, then the system can trigger an event to an administrator. The tracing is one of the most important aspects in a distributed system. So tracing helps you figure out the complete flow of a message from the point it enters in the system to the point it leaves out of the system. In a monolithic application, it's fine. You're always in the same system. But now you have many microservices catering a single request, so you have many remote connections. So if something happens, if something goes wrong, you should have a way to trace it back and find a root cause. So you need to worry about distributed tracing, and there are distributed tracing systems like Jaeger or Zipkin, so you need to have those systems in place. Then the immutability, right? So immutability is an aspect, a key property of containers, right? So if your servers are immutable, then at any point you can kill a container and spin it up, having no or minimal impact on the overall system. So immutable servers will not maintain state or even maintain stuff in the underneath file system. So you can simply wipe off a container and spin up a new one. So in terms of security, we maintain access control lists and policy decisions, right? So you need to make sure, or you need to absorb those requirements into your security design to see how you do that in an immutable manner. Then sharing user context. Right? In a microservice deployment, there is no shared context. Whenever one microservice talks to another microservice, you need to make sure you pass a user context. And this user context should be passed in a reliable, trustworthy manner so the recipient microservice can validate it. Then the polyglot architecture. So with polyglot architecture, you may have multiple microservices developed in different programming languages using different technology stacks. So that means you need to have security expertise in all those stacks. Right? In a multi-team environment, you need to have security experts in all these teams who know how to define security standards and best practices for their development teams. And also find out what are security scanning tools, static code analysis, dynamic testing stuff, and see how to integrate those stuff to the build system. So that's once again a challenging aspect in doing a security design for microservices. Okay, so let's focus on edge security. So this is the very common pattern that we see in a microservice deployment when you want to expose your microservices to the outside world. So there can be microservices, just private microservices. You don't need to expose those to the outside. So those would be just internal, but the microservices that needs to be accessed from the outside world, you expose through an API gateway. Right? And all the other systems, it can be a client or a system accessing on behalf of itself or a system accessing on behalf of a human user, all of the requests will go through the API gateway. So once again, this is a good pattern. This, to some extent, solves the multiple entry point problem, right? But once again, so there are different school of thoughts. People worry about having a central API gateway because once again, if you have one monolithic API gateway, we are moving back to the monolithic designs. To overcome that challenge, people use multiple API gateways. Like for example, if you have multiple departments, multiple teams building their own microservices, then probably each team may have their own API gateway. And all the microservices they develop would be behind that particular API gateway. So this is designed similar to what Netflix has. So they have their sole API gateway, and then all their microservices are behind that. So microservice, one microservice would talk to another microservice directly, and all the requests coming from the outside world will go through the API gateway. So here you can see only the foo microservice exposed to the outside through Soul. The other microservices, bar and C microservices, so they are just internal microservices. And how do you secure the edge? The recommended approach is to use OAuth 2.0. So I'm not going to talk about OAuth 2.0 here. I guess you are familiar with, and even the previous session had a good introduction to OAuth. So OAuth 2.0 is a best practice or the best approach that we would recommend for securing microservices at the edge, because this fits nicely there. Either like none of the APIs or the microservices are directly accessed by humans. Either they are accessed by a system or by a system on behalf of human user, right? So it's very rare a human will come and access a microservice directly. So that's why OAuth fits into this picture nicely. Okay. In OAuth, so normally most of the deployments they have the reference tokens. So it's an opaque token. When you send a reference token to the gateway or the resource server, it always has to talk to the token issuer or the authorization server to validate the token, right? Because it's an opaque token, resource server doesn't know anything about the token. Now, this adds an additional call, right? So each remote call that you make in a microservice deployment is really important if you can avoid it, because those calls, they have an impact in the latency. To avoid that, we can use self-contained access tokens. So a self-contained access token can be verified at the resource server end just by verifying the signature. It's a JWT. Right? You don't need to talk to the authorization server all the time. But this has a disadvantage too. If it is a reference token, and if it is revoked, right, then the resource server knows that it is revoked because every time it validates the access token, it has to talk to the authorization server, and authorization server knows it's revoked. But in case of a self-contained access token, if it is revoked, resource server doesn't know because it is not going to talk to the authorization server. To fix that, there are two approaches. So one is make the expiration of JWT or the self-contained access token very low, right? So you minimize the impact. The other approach is implement a way to propagate revocation decisions from the authorization server to the gateway layer, right? So if you take Netflix, so Netflix is using short-lived certificates to secure the communication between microservices internally, right? So the expiration of certificate is like 4 minutes. So that means they need not to worry about the revocation. They don't check whether certificate is revoked or not. They simply check whether the certificate is expired or not, right? Because revocation itself is a bit tricky. Okay, so this is the end-to-end flow. So here you have the end users who are accessing a client application, a web application through an authorization server. It can be OpenID Connect or SAML. And based on the token that you get, you can use a grant type like SAML grant type or JWT grant type and get a token from the token issuer or the authorization server trusted by the gateway. So here you can see there are two servers, right? So one is the authorization server and the token exchange. So the API gateway trusts the token exchange, but not the authorization server. So if you are to access an API to the API gateway, you need to bring a token from this particular token exchange, right? So once you pass that token to the gateway, gateway will talk to the token exchange, and based on the trust relationship, it will validate the token, that it will create its own JWT, which is signed by itself, and pass that back to the API gateway, and API gateway will pass this token to the downstream microservices. So these downstream microservices, they need not to trust the authorization server. It can be internal authorization server or even an external authorization server, but they don't need to trust that. They only trust their own internal token exchange. And then again, if you are crossing trust boundaries, right? Even in a single microservice deployment, there can be multiple trust boundaries. So if you cross trust boundaries when you do service-to-service communication, you need to make sure you get a token from a token exchange which is trusted by the recipient microservice. Okay. So we discussed this to some extent. So there are two common approaches. One is to use mutual authentication. The other one is to use JWT, right? So these are the challenges if you use mutual authentication. So you need to have a way to bootstrap trust between different microservices. There should be a way to provision these certificates to different microservices or workloads. And you need to have a way to rotate these keys, right? Revoke these keys. So you need to worry about all this stuff. So it's painful. So how do you fix that? So SPIFFE is one approach. It's a project which is targeting to fix this bootstrap problem in a platform agnostic manner. So have a look at that. So due to the time constraint, I'm not going to detail. So this is a very promising project. Have a look at the SPIFFE, and they have an implementation of SPIFFE specification called Spire. So check this out. So this is how SPIFFE works, but I'll skip this slide for the moment. Then the other approach is JWT, right? So JWT, I guess many of you are familiar with JWT, but if I briefly explain it, it's just a container of set of claims that you can transport from one place to another place. But the precise definition of a JWT would be, it is a JWS, that's JSON Web Signature, or a JWE, JSON Web Encryption, when they use compact serialization, right? So JWT is always compact serialized, and it has a set of claims. And so here you can see a sample JWT, which is a JWS in this case. You have three parts in here. The Husey header, which defines the strength of the the signature algorithms and some metadata. Then the payload, and finally the signature. So the JWT can be used to pass different claims different attributes, user context between microservices. Okay. So self-issued access tokens. Right. So self-issued access token would probably replace the mutual authentication in a microservices service-to-service authentication flow. It has the same strength, right? So each microservice has to be provisioned with a set of key pair, right? Now use that certificate or the key pair to build their own JSON web token and sign it and send it over the wire, right? So instead of doing the TLS mutual authentication at the handshake, the recipient microservice has to validate the signature of the JWT. The benefit here is you can send some custom claims. If you use TLS, mutual TLS, then you need to send those custom claims in just HTTP headers. So you cannot specifically as soon as, if you rely just on TLS, as soon as your message leaves the channel, it's no more protected, right? So if you use JWT here, you get the message level protection. Yeah, so maybe I'll skip this slide for that. Okay. So access control. So there are two approaches that you can do access control in a microservices deployment, right? At two levels even. So you do access control at the gateway level, right? So it can be the way you normally do for any APIs. Then the second level is at the microservice level, right? Now to do access control at the microservice level, you can follow central PDP approach where you have a centralized policy decision point and all the policies are defined in this centralized PDP. So whenever a request comes to a microservice, it intercepts that, then it will talk to the centralized PDP or wire and see whether there is an authorized request or not, right? But once again, with this approach, there's a remote call. It's a cost. It adds the latency to your entire flow. The second approach is embedded PDPs. So in here, the policy decision points are embedded into each microservice, right? And you have a central policy administration point, so this can be managed by each team, and it will push policies to the embedded PDPs, right? So this can be done in a pull model, where each microservice, when it spins up, it will register or subscribe to a specific topic of their interest in a messaging infrastructure, right? When there are policy updates, the policy administration point will publish an event to that particular topic, and that will notify all the interested parties or the microservices. Then they can pull the corresponding policies from the central policy administration point and populate the memory. And then again, we need to design this infrastructure in an immutable manner, so you should not try to persist these policies. You can just keep these policies in memory. If one microservice or the container goes down, when it boots up, you can simply talk to the central policy administration point and get all the policies that you need and populate the memory. Okay. So finally, deployment, right? So I assume all of you are familiar with containers and Docker, right? So containers build an abstraction over your local machine, and then Kubernetes, it's a container orchestration framework which makes an abstraction over the network, right? So Docker makes an abstraction over the machine, then the Kubernetes makes an abstraction over the network. Another good thing about Kubernetes is it introduces another level of isolation. That is the pod, right? In a pod, in a Kubernetes environment, you can have multiple containers. And all these containers are deployed in the same physical machine. So that's a pod, a group of containers deployed in the same physical machine. So that means, so the most common deployment model is you have one microservice per container, right? So that means you have multiple microservices in the same pod, in the same physical machine. Then when they talk to each other, the communication cost is very low because it's just within the same physical machine, right? So this can be used to implement something called sidecar pattern, right? So everything we discussed so far, application developers need not to worry, right? So that can be handled by a sidecar. So sidecar is another proxy, another microservice which runs co-located with your microservice in the same pod, right? So you have your main microservice, then a sidecar microservice. Good example of a sidecar would be a proxy. It's another microservice. So all the requests come into a microservice would be intercepted by this proxy sidecar, and it will do the security validation. So your application developers, they need to worry about that, right? You do the security validation for inbound requests, and also it can handle the outbound request. If your microservice wants to access another microservice, then as an application developer, you need not to worry about the security. You can define policies at the sidecar proxy, and it will attach the required security tokens for that particular microservice to the outbound request, right? So this is a sidecar concept. You have the main car, then you have a sidecar, which is co-located in the same pod, right? So if you look at this diagram, right? So in a typical microservice deployment, we see two planes, a control plane and a data plane. So your proxy, in this case, Envoy. So Envoy is a proxy developed by Lyft. It runs co-located with your service in the same pod, right? So all the requests are intercepted by the Envoy proxy, and then it talks to the mixer here, which basically builds the authorization policies and authorize the request and send the decision back. And if it's all fine, Envoy will let the request hit the service. And also, if service A wants to talk to service B, it will once again go through the Envoy proxy, and it will attach the security tokens required to access the other microservice, right? So control plane defines the required policies and other stuff, and push those stuff to the proxies in the microservice deployment. So this is the Istio implementation, right? Istio is so this pattern is called the service mesh pattern, right? So if you are from the SOA world familiar with ESB, think about like the service mesh as a lightweight like ESB, right? So now you have proxy running with each microservice, and this is a sidecar. So this is the service mesh pattern. So service mesh pattern is not just about security. You can implement resiliency features, and then again routing stuff, monitoring stuff like observability features, all can be done at the proxy level. Okay. So this is a security sidecar based on standards, right? And then again, building these quality of service features as sidecar has another benefit, because this doesn't bind into a specific implementation or language, right? This is another microservice. So your microservice can be written in any language, but still can use the same sidecar proxy, right? So here you can see like it's a security sidecar which exposes all its functionality through standard APIs. Like if you get a token, then basically the microservice can talk to the security sidecar to validate it, and if it is valid, it will let you go in, right? And also there can be multiple sidecars in the same microservice deployment. Yeah, so this is a service mesh pattern. So we discussed about this already. Okay. Yes. Any questions? Sorry, I had to speed up. So if you have any questions, like I'll be outside. We can meet and discuss. Maybe I can take a couple of questions if you need. Any questions? Okay, thank you very much.